Good morning. My name is Deanne Cameron. I am the head of Division for Nuclear Technology Development and Economics at the Nuclear Energy Agency, which is headquartered in Paris, France. It is my pleasure to be addressing the Suruga International Symposium, and I would like to extend my thanks and appreciation to our hosts MEXT for inviting me to provide some remarks on the future of nuclear energy. Next slide, please. I'd like to start by setting out some context for our discussion about the future of nuclear energy. And that context is the challenge to decarbonize the world's electricity systems to reach net zero by 2050. We know that the nuclear sector already plays an important role in mitigating emissions of carbon into the atmosphere, but we also know that it must play a significantly larger role by 2050. We have a publication at the NEA that we released in 2022. You can see the URL on the screen. I encourage you to download it, where we start to look at what is the potential role that nuclear could play in reaching net zero targets by 2050. And I won't spend a lot of time here because you can download the report and look at the details yourself. But the most important takeaway is that we find through our analysis that nuclear energy should triple. Its global installed nuclear capacity should triple by 2050 in order to play the role that it can and should contribute to net zero. This is an ambitious target to triple by 2050, but it is achievable. It is only achievable, though, if we look at all of the different roles that nuclear energy can play through a combination of long-term operation through refurbishment and maintenance and long-term operation of the existing fleet, as well as new build of generation 3 reactor technologies, gigawatt scale reactor technologies for on-grid power generation, and small modular reactors and advanced modular reactors for a combination of power and non-electric applications. Next slide, please. It's really important for us to be thinking of the future of nuclear energy as a portfolio. Again, a portfolio of long-term operation, gigawatt scale new build, small modular reactors for a variety of power and non-power applications. I'm going to focus my remarks today mainly on small modular reactors and advanced modular reactors, but I always like to contextualize a discussion about SMRs and AMRs in the bigger context, because SMRs complement LTO, long-term operations. They don't compete with long-term operations. New builds of gigawatt scale reactors don't compete with long-term operations. They don't compete with SMRs. We need all of the above. Next slide, please. The simple reality is that even in a very high renewables scenario, there will be hard to abate sectors where nuclear, and in particular SMRs, have an important role to play. And we see significant potential for small modular reactors to help replace coal on grid for power generation, to help replace diesel off grid for remote communities and remote mining sites, but also for the production of high temperature steam for industrial customers, and also for the production of hydrogen and synthetic fuels. Some of our member countries are looking at the potential for SMRs to replace bunker fuel for marine merchant shipping, which could be a very large market. It's a little bit more speculative, but we do have member countries that are looking at that possible application in a very serious way. Next slide, please. So having spoken to the need for global installed nuclear capacity to triple, having spoken about the role that SMRs can play in that overall tripling function of nuclear, let me now turn to the status of SMR deployment around the world, which gives us a sense of the direction the sector is headed into. First, this is a global sector. This is a global footprint. What you see on the screen right now are the headquarters of 42 of the SMR companies that are developing technologies. And some of them have already deployed, others are working towards commercialization and towards deployment. But clearly, you see a lot of activity all over the world. Next slide, please. This slide shows you the status of siting. So the previous slide was headquarters of those companies, and this is the status of siting of SMRs around the world. The color legend, the lightest shades of green and yellow are places where SMRs are already either under construction or operating, generating electricity on the grid. And the darker shades of blue are places where siting activities have begun, whether it's feasibility studies or site characterization or site preparation. So you can see here that in Russia and China, we have SMRs that have already been deployed and are generating electricity on the grid, both on land and on water. But you can see a lot of siting activities, for example, in North America and in Europe, where we have this sense of a wave of SMRs that are near term going to come into commercial operation. And this gives us a sense of what the future of nuclear is going to look like. It's going to have a significant representation of SMRs around the world. Next slide, please. So I've been talking about SMRs, but what is an SMR? It can be a lot of different things. And of the 42 reactor concepts that I've put on a map for you just now, they are different types of technologies. Some of them are water-cooled, some of them are gas-cooled, some of them are fast spectrum. There are some micro reactors and some molten salt reactors. So we are seeing a variety of SMR concepts under development towards deployment. Next slide, please. We're also seeing a variety of configurations. So the vast majority aim to be deployed on land. Some of them are multi-module configurations. And this has implications for scalability. It also has implications for the regulator. It represents this concept of multi-modular design, represents an innovation in engineering design. Some of them aim to be, or have been, deployed on water, marine-based. And a few of them even aim to be mobile and transportable. Next slide, please. Further emphasizing the point that we were talking about a variety, a range of different types of technologies, we're also talking about a range of fuel cycles. And here what you're seeing is across the horizontal axis, a range of sizes from micro reactors at around 5 megawatts electric, all the way up to larger SMRs and some even larger than 300 megawatts electric. And across the vertical axis here, we are showing you the levels of enrichment that these reactors envision using in their fuel cycle. You can see quite a few SMRs clustered around or just under 5% levels of enrichment. In other words, they're planning to use low enriched fuels, many of them planning to use fuel that is very similar or the same as the fuel that is commercially deployed for light water reactor fleets around the world today. And there's lots of good reasons why they might want to do that. Those fuels are already qualified, regulators are already comfortable with them, the supply chain is already there. But there are advanced reactors and other technologies that are planning to use higher levels of enrichment. And you can see a range of them that plan to use enrichment levels between 5 up to and very close to 20% enrichment. And that puts them into the category of HALEU, or high assay low enriched uranium. And these reactors are planning to use new fuels to achieve either higher levels of efficiency or higher temperatures or fast spectrums, any number of possible benefits, but they will face some challenges in some cases with the availability of that fuel and the need to create new fuel supply chains to meet their needs. Next slide, please. So again, driving home the point that we're not talking about one technology for one application. We're talking about a range of sizes and a range of temperatures. Across the horizontal on this graph, we plot the sizes of the SMRs that we are tracking at the NEA. And on the vertical, we plot the temperatures. And you can see temperatures ranging from 285 degrees all the way up to and exceeding 800 degrees Celsius. We've also shown on this graph some dotted lines in different colors to show you the temperature requirements of different industrial customers, paper and pulp, soda ash and potash. And then we've got the chemical sector, including refineries and ammonia production. and higher temperatures required for aluminum, steel, steam, methane reforming, and then above that, in the red line, steel, glass, ceramics, and cement. We have not shown any of the reactors that are the very high temperature reactors that are aiming to get up to and above 1,000 degrees Celsius. We don't consider those to be near-term deployment ready. Everything on this graph we do actually anticipate is nearing readiness for demonstration, deployment, and commercialization. And so you can see very clearly that we are expecting a range of technologies to satisfy the needs and to meet the needs for a variety of market applications. And that is both a good thing and a challenge. It's a good thing because the challenge of reaching net zero is about much more than just decarbonizing our electricity sources. It's about abating those otherwise hard to abate sectors. It's about providing heat, creating synthetic fuels at different sizes, on-grid, off-grid, and so on. So in that sense, this variety of technologies, range of sizes, temperatures, fuel cycles, configurations, concepts, is a good thing. But it also represents a significant challenge. In particular, it represents a challenge for regulators who need to ramp up their human resources and expertise in specific technologies and may find it challenging if they are faced all of a sudden with 20 applications for 20 different reactor concepts. It's a challenge for supply chains. It's a challenge for fuel supply chains and for the education pipeline that is training talent and training people to work in the sector. So that's sort of the backdrop. Now, how do we make sense of all of this? Because there's a lot going on. Turning to the next slide, please. How do we understand and predict which of these technologies will succeed? How will they succeed? And which ones are going to drive and shape the future of nuclear energy around the world? The diagram shown on the slide now is taken from the NEA SMR strategy, and it is a visualization of how we think about the overall challenge of SMRs, from technology development, so that's research, development, demonstration, and safety assessments for a variety of reactor concepts and reactor configurations. That's the technology push side of the equation, all the way through applications and markets, where in the green, we're recognizing the market pull side of the equation, where there's demand on-grid, off-grid for heat, district heat, for desalination, for the production of synthetic fuels and hydrogen, and so on. But what is it that's going to connect technology push to market pull? We call those the enabling conditions. These are necessary conditions for the successful deployment of technologies into new markets. There need to be enabling policy frameworks, regulatory pathways. Fuel cycle needs to be ready, both on the front end and the back end, with waste management readiness. There needs to be a supply chain and infrastructure, a talent pipeline. Public trust is an important enabling condition. And of course, the economics need to work and the financing frameworks need to be in place. So this is a framework for how we think about SMRs and what it's going to take to succeed with SMRs. And it is this framework that informed the development of the NEA SMR dashboard. Turning to the next slide, please. We set as an objective for ourselves at the NEA to create a dashboard that would help establish and contribute to some situational awareness about the status of SMRs. We clearly see that there's a lot going on all over the world, but how do we make sense of it? It's about more than just technology feasibility. Thinking about the technology readiness level, or the TRL, is useful, but it really only tells you a small part of the story. And we need to think about progress in these additional areas in order to really understand which SMRs are moving towards deployment quickly, efficiently, effectively, which ones are going to succeed. So at the NEA, we undertook to define 6 additional indicators of progress in the areas of licensing readiness, siting progress, fuel availability, financing, supply chain readiness, and public engagement and trust. Turning to the next slide. I won't go through them in great detail in my remarks today. You can find them in our publication on the SMR dashboard. But essentially what we've done is for each of these 6 indicators, we've defined a criteria that determines how much progress any individual SMR has made in these different areas. How much progress have they made on licensing, on siting, on financing, and so on. And from light green, where there has been no progress, and maybe you would characterize it as a paper reactor that exists only on paper, all the way through to dark green. And at the darkest shade of green, we are seeing that we're measuring progress towards the first commercial deployment. So first of kind commercially deployed. So if you have a reactor that has green all the way around, that is being commercially deployed. And then the shades of green in between to measure progress from non-binding commitments and lab scale work through contractual commitments and significant progress towards commercial deployment. So that is the intent of the 6 criteria. They're well defined in our publication. Let me show you what it looks like on the next slide. Here, we've pulled one of the SMRs to show you. On the next slide, please. This is a reactor that I'm sure will be near and dear to your hearts, the HTTR, which shows excellent progress all around. Of course, it's already operating. And so you can see we show it visually as a circular plot, but also the gauge graphs that show the progress. And on the right-hand side, we tell the story of the reactor across these 6 dimensions of readiness. I encourage you on the next slide, here is the QR code. Next slide, please. Here's the QR code to take a look at the report. We've assessed 42 reactors so far to date, and there's really a tremendous amount of momentum, but some reactors are moving faster than others. Please do check out our dashboard to see. We think that SMRs are going to be a big part of the future of nuclear energy. In 2024, we'll be updating our dashboard and moving to a digital platform, and we look forward to sharing that with you then. Next slide, please. I have 3 final slides. I'd like to bring it back to where we started, which is SMRs within this context of the full role of nuclear energy in reaching net zero. So SMRs making a contribution alongside gigawatt scale new build, alongside refurbishment and long-term operation of the existing fleet in order to triple global nuclear installed capacity by 2050. Turning to the next slide.
At the NEA, we were delighted to recently convene the first ministerial meeting called Roadmaps to New Nuclear, where we had 20 member countries and 40 CEOs come together to talk about not only SMRs, but also long-term operations, also new build of gigawatt scale reactors, and the challenges that we face collectively in reaching the target of tripling global installed nuclear capacity by 2050 for the very ambitious pursuit of net zero.
It was an important ministerial meeting. The timing was at the end of September, and it really was trying to set the stage and create a lot of momentum for COP28. We at the NEA will be present at COP28 in Dubai later this year, where we will be supporting countries that seek to pledge to triple global installed nuclear capacity by 2050. So we expect to see some communications around that objective to triple by 2050. And at the NEA, in support of that, we will be launching our initiative on accelerating SMRs for net zero. Next slide, please. And with that, that concludes my remarks on the future of nuclear energy. I hope that you found this interesting, and I wish you a very, very informative and successful symposium. Thank you.
ディアン・キャメロン様からのビデオメッセージをご覧いただきました。ありがとうございました。